Welcome to this explainer from Forge College. We are covering how to deploy and optimize on Solana Mainnet. Grab your helmets and strap in because today we are setting a serious rocket launch vibe for our final Mainnet mission. We're taking all the prep, all the code, all the strategy we've built, and we're finally executing a full deployment and optimization right on the Solana Mainnet. It is officially time for the capstone.
Okay, let's just acknowledge the elephant in the room. We have all been there. That universal, sweaty-palmed terror every developer feels right before pushing code to production. You know the feeling. Your heart rate spikes, you question literally every line of code you've ever written, and you just stare blankly at that massive deploy button. But hey, don't worry, because we've done the prep work. We're going to replace that panic with a clean, procedural, step-by-step launch sequence. So, to understand exactly where we are in our journey, let's look at the timeline. In our previous lesson, we laid the groundwork with monitoring and compliance after deployment. We wired up our dashboards and we set up our alerts so we wouldn't be flying blind. Today, we are right here in the present mainnet deployment. We're taking that instrumented code and putting it live, and this perfectly sets us up for the future, where we'll dive into the lower-level magic of C-level execution. Here is our engineering blueprint for today's flight. We've got 4 core deliverables. 1. The deployment. 2. Validation. 3. Optimization. And 4. The rollback. Section 1. The deployment. CI/CD liftoff. All right, it's time to actually get our compiled program out of our repository and onto the mainnet. But how do we handle security during this automated process? We are definitely not just manually uploading files from our laptops here. Step 1 is absolutely crucial. We recover ephemeral keys. Inside our CI/CD pipeline, we securely pull our key pair from a secret, but just long enough to use it. Step 2, we explicitly target the mainnet-beta RPC URL. And step 3, we run the standard Solana program deploy command. Now, once that artifact is deployed, our pipeline completely scrubs the runner clean. That key material, it's totally ephemeral. It exists only for the deployment job and is immediately destroyed, which keeps our mainnet credentials incredibly safe.
But wait, we don't just dump our program onto the entire network all at once. We use what's called a canary rollout. Think of the old coal miners taking a literal canary down into the mine to test the air quality, right? If the canary stopped singing, they need to get out before things got worse. Well, in Web3 development, releasing to a restricted mainnet slice or a testnet first acts as our canary. It's this highly calculated strategy to limit the operational blast radius. If there happens to be a critical bug, it only affects a tiny, restricted fraction of our traffic, rather than taking down our entire user base.
Section 2, validation, checking the telemetry. So, we have liftoff, but we can't just walk away, grab a coffee, and assume everything's fine. We need to check our dashboard dials to make sure the engine isn't catching fire in orbit. Which brings us to the million-dollar question. Is anyone out there? We push the code, sure, but how do we actually verify that the application is reachable, functional, and talking properly to live mainnet endpoints? We answer that question with some really strict pass conditions. First, we run our integration smoke tests directly against the mainnet RPC and our brand new program addresses. Our pass condition here is non-negotiable. We must ensure exactly 0 failures in our output JSON report. 0. But testing the code isn't enough. We also have to test our alarms. We deliberately simulate alert triggers, like intentionally faking a spike in latency just to prove that our Slack or PagerDuty channels actually light up. Because honestly, if your alarm system is broken, you don't really have an alarm system.
To keep an eye on this continuously, we built a custom TypeScript health check script. Step 1, we connect to the RPC. Step 2, we fetch a target account. Step 3, we assert that the account size and state match our exact expectations. And hey, here's a fun tip. You can actually use an AI assistant for a little bit of vibe coding to refine this script. Just prompt your AI to quickly add Borscht parsing for your specific account layout and have it build in exponential backoff. That way your health check doesn't throw a massive false alarm just because of a temporary transient network hiccup.
Section 3. Optimization. Tuning the engine.
Now, it is not enough to just deploy a functional program. If we want to be true professionals, we have to prove that we can make the program faster and cheaper to run. Let's talk about costs for a second. Specifically, rent exemption and Lamport churn. You can think of these as the standard operating overhead. It's very much like paying monthly server fees in traditional Web 2. Over in Solana, maintaining state on the blockchain requires you to hold a minimum balance of Lamports, which makes the account rent exempt. If we're constantly creating and closing inefficiently sized accounts, we experience what's called Lamport churn. These costs are the absolute prime targets for our post-deployment tuning.
Transaction batching is a perfect target for this optimization. Processing one item at a time requires a massive baseline of RPC calls. But look what happens when we optimize to a batch size of 4. We see a dramatic drop in network requests. By simply grouping operations together, we drastically reduce our per-transaction RPC calls and lower our overall latency. As we always emphasize, optimization isn't just a theoretical exercise. It translates directly to noticeably better performance and much lower costs.
The absolutely crucial point here is that we must measure these improvements using a strict scientific method. You can't just deploy a patch, refresh the web page, and say, yeah, feels faster. Nope. First, we capture a reproducible 15-minute synthetic load to establish a rock-solid baseline. Then we apply our optimization. After that, we let the performance settle for at least 10 minutes under the exact same load before we capture the new metrics. This deterministic apples-to-apples before and after comparison is literally the only way to make evidence-driven engineering decisions.
Section 4. The rollback. The emergency abort button. And this brings us to the terrifying but completely necessary scenario where our optimization actually broke something. The telemetry alarms are screaming and we have to immediately reverse course. We live by this golden rule. Always have a rehearsed rollback. Release safety must be procedural. If everything crashes, you cannot be frantically searching Stack Overflow for how to undo a deployment. Your rollback procedure must be something you can execute completely blindly in mere minutes.
Let's map out that exact panic-free sequence for aborting the current version. Step 1. Your CI pipeline locates the previous known good program file right in your artifact store. Step 2. You redeploy that stable version via CI. Step 3. You automatically rerun your smoke tests against the restored version just to ensure the bleeding has actually stopped. No guessing, no manually typing terminal commands while your hands are shaking. Just a smooth, clean restoration to a stable state without dropping the system.
Section 5. Mission accomplished. The Artifact Bundle.
We have deployed, validated, optimized, and prepared our rollback. Now it's time to package exactly what you need for your final capstone deliverable. Here is your ultimate submission folder checklist. You're going to need your zero failure smoke test JSON report, your automated health check logs, and your CI run IDs proving the deployment happened via the pipeline. You'll also need those metric snapshot CSVs and an optimization diff report showing your 15-minute before and 10-minute after measurements. Finally, you must include your rollback runbook commands. And remember, keep those runbooks exact. Future incident responders, which, let's be real, might just be you at 3 a.m., should be able to literally copy and paste without having to interpret a single thing.
So, you've optimized your application's compute usage and deployment architecture. But you might be wondering, how does Solana actually schedule and parallelize all these transactions at runtime? Understanding this lower-level runtime engine is what separates good developers from truly great ones. And it's exactly what we'll explore in our next module on C-level execution. If you want to dive deeper into C-level execution, master compute unit contention, or really just continue your broader Web3 educational journey, make sure to visit forge.college to learn more about this subject and discover other amazing Web3 topics. Thanks for learning with us, and happy deploying.